Hi, everyone. Thank you and welcome to a session on IoT and machine learning. These are some of the hottest topics that are coming up, and it's really a pleasure to be talking about this on behalf of Intel and to a broader global community. So let's go ahead and get started. Let me see if I can share my screen and do this right. So welcome again. The the main topic that we wanted to cover today, right here, is the idea that machine learning is a powerful tool that can help a number of IoT applications. So I'll start with a bit of motivation in terms of what we are facing currently. So as many of you have heard, if you heard the excellent talk by Brian this morning and by many others so far, there is definitely a plethora of devices as well as data that is going to be covering all different domains that are currently of interest for a number of industries. So in this particular case, when we talk about data and things, we are talking about connecting the things to the cloud. The network that these things are connected to, it must be flexible, it must be cost effective, and there must be an element of analytics that needs to be present both at the cloud as well as at the edge. As we are going along, the last couple of years and furthermore have seen a tremendous amount of development in artificial intelligence, the ability for smaller devices to have the capability to run very complex models for inferencing. So we'll talk a little bit about that. And we'll talk a little bit about the fact that all of this is being driven due to the cost of sensors being down by a factor of 2. The cost of bandwidth is down. The cost of compute is down. But there is a growing disparity between the ability of the network to ferry the data, the latency with which it can actually cover some of the target applications. Those are the areas where there is a tremendous amount of interest in making sure that analytics at the edge helps bridge this gap. Okay. So a brief background about me. My name is Yashesh Shroff. So I came into this group at Intel almost by happenstance, essentially dancing around the edges, so to speak. My background is in micromirrors and sensor development. So that was the subject of my dissertation about a decade or so ago at UC Berkeley. And I'd always been interested in developing algorithms and models around optical pattern generation. So in the world of lithography, as we march to 18 nanometers, 14 nanometers, now 10 nanometers, it's increasingly important to use statistical optics as a way to get the pattern fidelity right. Well, some of these previous worlds are colliding again in this new age of IoT and machine learning, wherein you see some of the same mechanical as well as algorithmic approaches converging in this space. So I'm happy to talk about that. I'll start off with a quote that's actually been it's been very poignant, right? So Carl Steinberg, if you know of him, he's a pioneer in computer science, and way back in '66, he essentially predicted the age of Internet of Things. So I want to quickly talk about a couple of areas where this is really important. Number one, it's industrial manufacturing. Second, healthcare, transportation and logistics, retail, smart buildings, and energy and utilities. So I'll walk us through some of these key areas and help drive home the message that machine learning applications at the edge are not only needed, but they are sufficiently helpful to drive disruption in each of these industries. So I've created sort of a snapshot of areas where the potential of IoT and machine learning offer an array of opportunity to disrupt industries. Currently, these environments are pervasive with minimal edge intelligence, such as RFIDs or sensors. Adding the capability of local compute and memory is certainly opportunistic. So broadly, there are categories that I've laid out over here. So let's take a deeper look at some of them. So in the area of smart manufacturing and monitoring, the key insights that we should gather are improved manufacturing time, reduced operational expenses, and higher throughput. So if you're a factory owner and you're looking for efficiencies in both CapEx and OpEx, IoT and machine learning are areas for you to get more bandwidth and a competitive advantage. So to motivate this, let's take an example of M2M communications. Many of you may have heard of the fact that machine-to-machine communication is going to be the new paradigm. So it's very simply explained. So let's say you have an LED sensor, and the sensor is supposed to figure out how much ambient light is present, and you have a light bulb that essentially responds to that. The M2M communication protocols essentially take away the problem of the middleman, and they address issues of low latency around energy efficiency. So establishing rules engines is critical here. So if you want to have some changes that, okay, well, right now the amount of light that is required to turn on the light bulb is not sufficient, you do not need a developer to go and change the algorithm, right? So the user experience is key here, and having a complicated model driving automation at the edge will only be good as long as there is a decent user experience there. The second is on maintenance and cost savings. So preventive maintenance at a regular cadence can be replaced by maintenance at a cadence that is more cost beneficial. In coming from the world of TMG at Intel, there is certainly a lot of focus that we put in to the preventive maintenance aspects of our manufacturing. Moving to something like predictive maintenance that not only can increase the uptime of our tools, but also provide a greater flexibility around knowing when the tools are going to be down so you can plan around it, is tremendously beneficial, along with the OpEx benefits. Then you have the flow optimization. So if you've been to a factory and you've seen these candies, or you've seen the welding machine doing its job, and it's constantly cranking out products, you need to be able to know how the chain of equipment along the way is performing. And so any planned downtime needs to be taken in the aggregate. And finally, the ability for the factory owner and also the company management to know in real time how the factories are producing goods, how they're keeping up with demand, is essential. So here is a tool that I really like. It's Grafana. It's an open source visualization tool, and it's able to pull in time series data from a number of sources. So we'll talk a little bit about this a little later. But these are essentially the tools that allow you, along with the likes of Tableau, Microsoft BI, and others, that allow you to gain insight into your data. The second example here is of healthcare. It is no secret that the US healthcare industry is overpriced, inefficient. So a while back, I think it was 4 or 5 years ago, there was a report done that talked about the fact that the US was spending around 2.6 trillion in healthcare each year, out of which 600 billion essentially was cost on treatments that either do not help or actually cause harm. So the challenge in healthcare is to correctly identify, track, and document patient care to provide timely, accurate, and improved quality of treatment. And to overcome that, the idea that smart, non-invasive technology can be implemented to provide real-time and accurate tracking of data becomes really important. And it creates a feedback loop that's necessary for the providers and the payers to work with the patient. One of the examples that I like to talk about over here is the one by United Healthcare. So a while back, they worked with some hospitals to remotely monitor patients at home. And this was done with tablets and Bluetooth connected devices. And the program showed pretty significant benefits, right, in terms of reduced medical costs and hospital readmission rates. Okay. The second thing that is also important really here is around the asset tracking that happens in hospitals. So there's a strong need to even track simple things like wheelchairs and also to monitor things like air quality. So when a patient is in ICU, for instance, and is supposed to go into the operation theater or vice versa, real-time tracking of the patient along with the staff, so where the doctors are, can be very important. The current paradigms of paging are there, but there are tools that can actually significantly improve the workflow. So tracking of motion through choke points, as you can see over here, and access to designated areas, as well as materials tracking, for instance, to prevent surgical tools being left behind in patients, is a surprisingly disruptive opportunity. Security and streaming protocols are certainly very important over here as well. And so is data aggregation, by which I mean the ability to pull automatic data collection automatically, essentially helping with the triage paperwork and getting the experience of the patient in the hospital much better. The other thing that the patient tracking and the movement tracking that does is that when you have movement to recovery, so there was a recently a study done that showcased the ability for the patients to move earlier than was actually guided by previous practices. And they found out that post-surgery, moving certain patients around a little bit sooner than they otherwise would have and monitoring that through these wearable devices was actually of significant benefit. Okay, so I have just a couple of other examples and I'll quickly move into the machine learning portion as well. So again, in smart buildings, you have advanced sensors that have a critical role to play in transforming facilities into intelligent buildings, because these devices can capture, communicate, and in some situations even analyze crucial energy and operational data, right? So you can now, if you're a building manager, a building owner, and you're leasing it out to tenants, startups, or what may be, you can now start to differentiate the building space for your tenants. You can start to meet efficiency standards and get significant cashback from the government for being more green. The user experience is certainly improved. And obviously, same as with other sectors, operational savings are significant. So temporal space utilization in smart buildings is actually really picking up. So we are able to now see, as the day moves along, how the flow of traffic is essentially going from one portion of a building to another portion, closer to stairwells, closer to elevators, around noon, lunchtime. So how is actually the flow moving? Where are things actually being obstructed? Which areas are not being utilized? Conference rooms. If you have a 20-person conference room and only a couple of people are actually using it, then you know that this facility can be made a little bit better by rearranging the layout in future revisions. Water savings and maintenance. Again, the ability of not developers running this, but folks who are actually on the operations side and OT having a say in the information technology uh, side of things is going to be very critical. This is also an area where you start to see some level of clash that's happening, right, between operations and IT. So now coming to the theme of the talk, right? So at a high level, there are two major challenges over here. That is connecting legacy devices to the internet and ensuring that all IoT and M2M communications are seamless and secure. So the Intel IoT gateways, and there are other gateways around as well, they serve machine to machine and the mobile environments and interoperate with essentially any messaging appliance, right? Whether it be CoAP, MQTT, Kafka, you name it, right? So let's take a look at this somewhat more carefully, right? So you have a bunch of devices essentially sensing the environment, vibration, humidity, temperature, you name it. Some of these devices have already built-in Wi-Fi connection or Zigbee or Bluetooth connection and can communicate directly to the gateway. Many other devices are starting to be brought in from brownfield to greenfield, and they're connected to these microcontroller units. And this is pervasive, starting to be pervasive in pretty much every industry that's out there, right? So the goal is that up until now, we noticed what the temperature, vibration, etc., was in all of these areas, right? That's why these protocols have actually existed since the 70s, right? But the fact was that this was now being pushed out onto a PC, and finally somebody would actually go to the machine and change a setting, right? And the whole aspect over here is that we're trying to automate this entire behavior at the edge. How do you do that? So practically, the microcontroller units, which are connected to these sensors, and there can be anywhere from 1 to 20 sensors on an ultrasonic welding machine, for instance. These sensors are constantly monitoring time series data. The time series data is being transmitted at the rate of hundreds of thousands of messages, right? These brokering services that run between the microcontroller unit and the gateway, or between the sensor and the gateway. And the gateway is then able to run a number of things over there. So we are now looking very closely at a couple of technologies at the gateway itself. I've mentioned Docker over here, but the Intel Clear Container technology is really fantastic. So while stuff like Docker may run on top of a virtual machine, the Clear Container technology can actually run on bare metal hardware, giving you a significant bump in the compute efficiency, but at the same time, it gives you the security of a virtual machine. So as you're running these separate services as either a database or a manageability service, a security service, or sensor middleware that connects to all of these sensors at the edge or connects to the actuators, you also have a number of analytics protocols that are running that are doing inferencing at the edge. And I'll talk a little bit about that, of course, in a moment. They're doing protocol conversion, right? So we talked about OT to IT transformation. So the legacy protocol that's sitting over here needs to be converted into RESTful APIs or HTTP or something that's more in vogue of Web 2.0, right? And the gateways are streaming data from literally hundreds of sensors, right? And it has the ability to do some level of data cleanup, data munging, and then it can send the data to the cloud. So here, the issue of this bandwidth limitation essentially comes in. So once the cloud side is figured out with a certain set of business logic rules, service orchestration, device attestation, you start to then figure out that, okay, when you take a look at cleaned up data, you need to be able to run efficient models on the cloud. So that's where, on the edge. And before you do that, a lot of training happens with a combination of a data lake, right, which essentially takes in streams of data from data stores, and it can be from any one of these services that are running on the edge. So Spark streaming, for instance, and Intel has an optimized version of Spark that I'll talk a little later about that can specifically help with machine learning. Cloudera, and we have notebooks out there that specifically talk about the combination of Cloudera and Spark streaming. Kafka is an upcoming, very rapidly evolving streaming technology. And you have the likes of InfluxDB or Prometheus that take a lot of heavy lift out of storing streaming data. The challenge here becomes that when you have streaming data that is time-stamped, you don't want to continue storing the same timestamp again and again, right, with some delta. So these databases are able to store the data in a very efficient fashion, and they can also be scaled up. And Grafana, I mentioned earlier, is an example of our visualization tools. So time series data is essentially not domain specific, right? I mean, there is economic, series data, marketing has it, industry, meteorology, biomedicine, genomics, right? So the idea for us here really is to take a look at predictive analytics. And by predictive analytics, what I mean is the ability to forecast behavior of the equipment given certain events that have happened in the past. And we're all familiar probably with weather forecasting. We utilize stock market prediction tools. But the example here that I can talk about is really, for instance, temperature in a building. So let's say you have a sensor that's constantly monitoring temperature in one corner of a room. And you have multiple sensors monitoring temperature over a wide, over a large portion of a smart building, right? As the temperature rises or falls, the decision that needs to be taken is whether the AC needs to be turned on. Turning the AC on requires a certain time lag, right? It's not instantaneous. And so you want to be able to predict what the temperature is going to be like once the AC is on. So you have your target value and you want to reach that target value. So if you do turn the AC on prematurely, and the temperature actually goes down, for instance, because it's evening and the weather forecast was that the temperature is going to be cooler outside, the building's expected to be cooler, well, you just wasted some unnecessary energy. On the other hand, if you wait too long and the building heats up, then again, you're causing disruption to the flow in the building. So these are some of the areas in which you start to see predictive analytics playing a pretty critical role at the edge. The other area where we actually consider time series databases to be of importance in analytics is on determining anomalous behavior. So more recently, there have been a number of papers by Stanford, and after this, once the PDF is out, you'll get a lot of those resources, which actually talk about novel algorithms that automatically detect anomalous behavior. But to do that, you can also start to think about it as non-anomalous in classification models, right? So for instance, data analytics can also have requirements around real-time and low latency reaction. So stream computing, as we mentioned earlier, is now getting more and more support from edge computing. Oftentimes, cloud latency is a 1 millisecond round trip, and then the workload in the cloud itself is not even included here, right? So if you're a car moving along pretty fast on a freeway, That's a sure way where you want to do analytics at the edge. But even if you are operating a heavy machinery and you find that the vibration is going out of norm, you may not have time to do a couple of hops over the internet to find out that, hey, by the way, how does my model actually look over here? You have to take some real-time decisions, and that can only be done efficiently at the edge. And of course, there are certain cost concerns also that are addressed here, which is in the savings in bandwidth cost. And sometimes these sensors are actually running on battery, right? If you slap on several different vibration sensors at different portions of my favorite tool I use for examples is a welding machine, ultrasonic welding machine, you start to see that there's a concern there. A lot of the data analysis is done on windowing of incremental time series. So you basically take a look at the last n seconds and you move forward. So here's an example of a time series model. So this is an example of an auto regression model. So when you take a look at this time series, for instance, and this is obviously clearly seasonal data, right? So from 1 January to the next January, you can see that there's a certain pattern that happens. So when you do regression of a time series data on a previous instance of itself, you essentially get auto regression. But the key over here really is in working with the error conditions. So the error condition in a single time series, right, is going to be is basically going to be white noise, right? And the dependent variable y, as it linearly regresses on x, the epsilon term is Gaussian. It's Gaussian normal. It's homoscedastic. And if you were to plot the errors, there would be no pattern to it, right, as a function of time. So time series models are essentially built around white noise. There are a couple of things that I would actually suggest by way of developing a workflow around this. Certainly take a look at the UCI machine learning repo. There's a very nice database there called the Sonar database, I believe. So this is from 1968, just to essentially get your feet wet. There's a very nice Kaggle competition on energy forecasting. This was, I believe, in 4 or 5 years ago, 2012. And so what you want to start doing with this, with these data sets is perform a cross-validation, a train and a test split, right? So I'll talk a little bit about that. Once you get the data in the cloud analyzed and a model built, and it can be done in any one of these languages, you can generate essentially what's called a predictive model markup language. It's basically kilobytes of XML file. You push this model to the edge, and now the edge device is able to run inference on streaming data. So there are a couple of tools that come in handy from Intel in this space. One tool I'll quickly talk about is, of course, Caffe and TensorFlow model generation. So that's our deep learning SDK. And you can easily find it online if you just do a search for it. I have a link here. And the second tool that I use a little bit more frequently is the standalone library for Apache Spark. It's the Intel CPU optimized MKL version. It's been open sourced, I believe, last 6 months or so, and it has all the benefits that you would want from a CPU, and you write in language and code that you're very familiar with. The third thing that's also very interesting from Intel that I should talk about is Intel Curie, which is essentially the pattern matching engine that we've developed and pushed out in a couple of products. So the Arduino Genuino products that you see for the US and the non-US version, and the tiny tile that you can get from Elements or any number of vendors outside, essentially run the pattern matching engine, which is basically now it's grown to be 128 parallel processing elements, right? So it takes, it can actually support features 32,000 categories in 3 classifications. So it just comes back with a certain probability and identifies the state of the unit as, for instance, a walk motion, a standing motion, a rest motion, a jog motion, etc. So there is an open Curie Open Dev Kit. I think I'm showing the URL here. I don't have it written, but again, very, very useful to look at. So this is, I wanted to quickly jump into a quick talk about machine learning. So this is an example of cancerous biopsies where machines are now starting to do as good a job as humans, right? The ability of machines to, run algorithms, to start, quote unquote, thinking for themselves, it goes back decades, right, to the 1950s and 60s when some of the initial work was done over here. So just like I had a quote with on IoT, I feel like I should have a quote on machine learning as well, which Arthur Samuel is phenomenally talked about. So the flow that, again, we talked about earlier, right? You have a lot of your training data that comes in from the edge devices. If it's manual classification or if it's a classification model, you essentially apply the label to it, you extract the features, and the algorithm is generated. So during the prediction timeframe or the inference timeframe, you do essentially the same thing, but you get the reverse of it out, and you have some level of certainty on the label. So the key things, just bare bones understanding that when you talk about machine learning, you have to split your data through a cross-validation platform. So if you are familiar with R and Python, NumPy, SciPy libraries, there are a lot of tools that allow you to automatically do cross-validation, and you'll do this again and again, right? And once you do this k-fold is, how many times are you going to do the cross-validation? You get a certain performance out of it, and that's what you essentially use as for selecting your final model. Okay, so machine learning can be supervised or unsupervised. There's a lot of resources out there, so I'm not going to talk a lot about it right now, but a couple of things that I would mention here is that predictive modeling, has a metric to evaluate how well a model works, right? And so it needs to be quantifiable. It needs to be objective. So typically we use root mean square error, RMSE, for such things. You don't often have the ability to have just doing a linear regression like the example that I showed earlier. So it is a binary response, for instance. Mathematically, you represent a binary response with a logistic regression. So you can see it right there. Finally, the clustered and unclustered data segregation. So this is all based on K nearest means, KNN type of algorithms. And then the type of algorithms, for instance, if anybody's worked on the Titanic data sets, decision tree classification, random forest comes in very handy, again, for classification purposes. So I actually created a quick model on, I often get questions around what exactly is a neural network. And so in a couple of minutes that I have, I'm going to quickly walk through this animation. So let's say you have an activation function, right? That tells you basically what the output layer is. And this is, again, going back to logistic regression, this is usually some sort of hyperbolic tangent function. And you have some input variables. For instance, given age, employment, and income of an individual, predict whether that individual is married or single. And so the model can have a couple of different variables that you have to decide upon, which is, number one, how many hidden layers are you going to have? And when you set your parameters up, your model behaves in a certain way. So the idea is that as you go through with the classification, you are establishing certain weights between the input and the output nodes here. And these neurons, it's essentially matrix multiplication, right? And that's why you're able to do really fast neural network inference, even at the edge. So if you take a look at one of Intel's, really good acquisitions, right, Mobidius, they apply a lot of vision analytics at the edge by taking a model from the cloud and then doing learning inference at the edge, essentially in a very rapid way. So this is again another example of handwriting recognition. So each digit that you have for handwriting is essentially split into a 28 by 28 pixel image. And the way this works is that all of these 784 neurons turn into input, and the output is 10 different neurons, right? And the question is, okay, how do you basically establish your model for that? So I'll stop over here and see if I can jump into the question answer sessions. If there's anything else, let's say, is there anything like the most widely used workflow between supervised workflow? So yeah, that's a good question. There are a lot of options out there, and certainly there's a flavor you could choose from. Specifically on supervised versus unsupervised workflow, I think Spark Streaming certainly is one that I've used more often. And I think it actually does allow you to get a lot more bang for the buck, because you're able to run it on a number of Spark clusters, especially if you're looking at training on a really large set of models, input parameters. Yeah, so Python is definitely is there. Python actually does work well with NumPy and SciPy. If you're a really true beginner and you're language agnostic, then my favorite is actually R, because it comes with this package called Caret, and it's let me just type it here, and it has a number of algorithms called, so for instance, GLM, cross validation, and others that allow you to very quickly. So I actually had one of these things running over here for example. I don't have time to go through this, but you can actually start to detect anomalous behavior on these things. So Caret, so Python actually has a number of advantages, right? So from a developer perspective, Python is essentially ubiquitous, right? So you can run it on very low power devices. The disadvantage with Python is that even with the likes of, and it's changing rapidly, but even with the likes of NumPy and SciPy libraries and other APIs that are being developed, right, on Spark Streaming, for instance, it still has many fewer libraries than R. R right now, I think, is sitting at around 7,000 or 8,000 different libraries made by statisticians. So if you're running a data science project, there are things like RStudio, which is a fantastic IDE that you can use. There is also R in the cloud, right? So you could run these tools as a service. One of the advantages is that it actually has a number of low-level packages that essentially take the guesswork out of model building. So especially as you're starting out and you're going into Kaggle competitions, for instance, and you're taking a look at these time series data that is emblematic of the type of data that you'd be working on IoT projects. For instance, I'm on a bicycle pedal, right? And now is the pedal moving at 10 RPM or 5 RPM, what's going on, right? So when you start to figure out analytics around this, and you want to do this very efficiently, it's important to try and understand, how the model is built out. When you go into production, R does offer you that ability as well. Let's see. Thank you, Peter. So any frameworks for edge analytics on Intel Gateway to train the gateway from cloud with minimal corpus on gateway? Oh, that's a great question. Yeah. So the in fact, this is a research area of mine as well, along with a couple of other things that I do. So you can certainly do that, as I mentioned earlier. If you actually go into just go back. So the ability of the gateway to run, with minimal uplift, right? So this Curie was essentially created for that. So you're developing, for instance, your model by walking around. You're taking a lot of training data from maybe hundreds of people and how they're walking around, and now you're pushing that entire model out as essentially a 128 byte input vector, right? um, uh, it's a matrix multiplication that happens. And so with something as small as an 8-bit algorithmic unit, you are very quickly able to assess what it is that is being inferred right at the edge. The second thing is that you could also use tools like Apache Spark, again, create the model. The way to do this is my money slide, right? The way to do this is, if you have gobs and gobs of data, certainly you may want to go with something like Kafka, streaming sources, or Spark, etc., right? Microsoft Azure has its own suite of tools as well in this space. Of course, I'm biased towards the Intel tools because I think that they offer a lot of value in efficient usage of compute. But certainly anything that's optimized on CPU does work well. If you don't have it, then don't worry about it, right? I mean, run simple MQTT examples and go with it. The examples are, and then have something like an inflex database that stores the time series data, generate your model, and then push it out. And you can have essentially a repository or a small storage on your gateway as well. So the gateway, where's my gateway slide? Yeah. So on the gateway, you essentially run agents for all of these things. You have a manageability agent, but there's a cloud orchestration service that's basically managing the gateway. Essentially, when the gateway is sitting at some corner of an office building, you don't want to go in with a USB stick and say that, okay, now let me update it from Ubuntu 16.04 to 17.04. Sensor middleware updates. So the orchestration services are great, but coupled with the ability to deploy them with containers, you can actually start to SSH or have the gateway generate a web interface as well, right? And it's completely secure because it's running the the Apache web server in a totally different container. So that's another area that we are taking a look at as well. So you have inferencing ability at the edge that's really important with a model that comes trained from the cloud. So yeah, Python is definitely a good choice for model for machine learning. If you are just now starting with coding, I will say that Python is significantly easier to get tuned to than other statistical languages. Another favorite of mine that's solving the two-language problem is Julia, and Intel has a really strong effort in terms of optimizing Julia for CPU as well. So you can do a lot of search on it online. And an alternative to coding, really, I mean, take a look at Node-RED. And if you can deploy Node-RED, for instance, on a gateway or on your Ubuntu machine, just take a look at it and run some sample code. And what you're effectively doing is you're turning. In fact, I had an example of Node-RED in my smart manufacturing, or maybe it was. Yeah, smart building. So this is an example of Node-RED, right, where you're basically taking these pieces of code blocks and attaching them together, and they're running in parallel. They're atomic in nature, and they're passing messages back and forth. So yeah, there's a lot you could do in that case. Yes, it doesn't do analytics, but it does do streaming and transformation. Thanks, Annie. All right, I'll jump back to my presentation now. I have a couple more things to cover. I really quickly went through the machine learning portion of this to essentially give everyone a flavor of what's done. But I'll keep looking at it. Okay, after you upload the model, is there a feature that allows you to verify the integrity of the model against a hack? You'll need to explain this a little bit more. The model, I mean, number one, I strongly recommend, right? And you have to take a look at the Intel security capabilities on the edge. So I didn't even get into all of that stuff here, but the gateway has a hardware root of trust if it's Intel x86 enabled in most instances, right? So you can take advantages of features such as enhanced privacy ID, and you're able to do a secure key exchange, so the key doesn't even reside in an open file system. If any of you, if you've worked on in that space, it's going to be important. So once you send the model through, you can do a checksum, you can look at the XML file, but if a third party I think you have to be sure that the third party is not violated the integrity of your deployment. And there are two other tools that you have to rely upon. But in and of itself, other than doing checksums and having ways to confirm that the model is running accurately, I'm not sure I can really answer that. Sorry. Okay. There's also another couple of things that I would talk about. So Stanford has the CS231 course. If you're interested in doing computer vision on the edge and deploying models, try and understand how neural networks can help with that. And you can actually use a very nice, user interface they have on the website, and of course learn the physics behind it or the math behind it through the course. Right? I'll run through this. My point really here is that the application area and the resourcing area is significantly complicated. There are a lot of players out there, but that only means that there's the higher need for standardization, and that's where Intel is really strong in working with these companies to develop these standards. I think it was talking about Node-RED, if you're talking about the compute modes. Okay. Yeah, I just had a couple of other things around that. Yes, you will get the slides. They're not completely polished, so I will be able to get them done by the weekend. And I think Be My App should be able, or with the best should be able to send out a link to everyone. So yeah, if you're in the Bay Area, if you're interested in working more of these things, definitely get in touch with me, and we'll try to support you. If you're a startup that has traction on the IoT side and is looking at machine learning, and my other role is also as a program manager, and certainly it'll be of interest to hear that. Arvind, I mean, the best way is just go ahead and tweet at me. Otherwise, my email is yashesh.a.shroff@intel.com. So you can either tweet me at the tweet I provided, and the email is my full name with A in between, yashesh.a.shroff@intel. Would you guys like me to go through the machine learning? I kind of breezed through it, but would you like me to go through any of the machine learning algorithms, time series algorithms in more detail? So the idea here really is that as you're taking a look at any time series information, the first focus, there are a couple of things that you could do, right? So if you're looking for fault detection, you can run a simple windowing operation over here, right? For instance, over the last 100 measurements, what was the mean, median of the data that has actually come through, right? So in this case, you can see that the mean is supposed to be flatly zero. But in case this jumps up, right, because one of the sensors actually dies, or it changes to something higher, then, or in another instance, it has half the value, then you're able to go beyond the UCL and LCL, the upper control limits and the lower control limits, and you're able to respond effectively. So IoT is all about, a village raising a child. I like to think of it that way. You need your UX experts to actually help the plant managers not rush into coding related issues. You need the subject matter experts who know the machines well and how they should operate, but not necessarily coders. And you, of course, need the coders and the IT infrastructures and the security guys to make sure that the model development, model deployment, the data storage, the insights are at par. And finally, from a business perspective, of course, all of this needs to have a certain ROI for you to use, right? So assigning behavioral patterns to your sensor streams, right? Uh, Classification might be an easier way to think about things, uh, in vision learning, for instance. But I think that for time series, it's really, really difficult because human eye, at least I can't just look at a waveform and say that, okay, somebody's jogging or somebody's running. And it's also really hard to basically move the tools, endpoints around to do just that. Thanks again, everyone. Bye-bye.